this thing? Okay, got it. Okay. Hello, everyone. My name is Justin Chang. I am currently a postdoc at Rice University working under Matt Knepley, but very soon I'll be moving to National Renewable Energy Lab. And so today's presentation will be over a performance spectrum based on the TAS analysis. And this is something Matt and I have been working on over this past year. Okay, so basically, when it comes to high performance computing, there are a lot of factors that may affect the performance of software and algorithms like PETSc. So like there's things like hardware utilization, data structures. So as Richard mentioned 2 days ago, like one of the key performance things we have to be aware of is how you place processes on your computer architecture. And also you have to be aware of what kind of data structures you're using and just understand how you're, I guess, utilizing caches or you're utilizing just your resources efficiently. But the thing is, the question we all want to know is how high performing are these software and algorithms? Is the time to solution fast or is it slow? And if you're a domain scientist like myself, you probably don't have the time to really dissect the source codes and really understand everything. So for people like me, it would be kind of desirable to have a performance model to kind of understand performance-related questions in terms of like time to solution, arithmetic intensity, flop rate, etc. And so just some other things that people have done in the past to answer these questions. So there are some notable tools and methodologies like the Stream and PAPI software, and then there's also mentioned also on Monday, there's like the roofline model and then the perfect cache model for SBMV. And then also some people have developed these sophisticated parallel debugger profiling software like OpenSpeedShot or the HPC Toolkit. So they're all really good for looking at performance with respect to hardware. But like if we're solving PDEs, well, we also want to know how algorithmically efficient our solvers and software are. And so more importantly, how do they scale when we bring them to like real larger size problems? So what I did in my PhD, my last chapter, was I introduced something called the performance spectrum, also with Matt Knepley. And so this performance spectrum looks at three metrics. It looks at, of course, the time to solution. It looks at some form of intensity. In our case, it is the arithmetic intensity based on hardware counters. And then lastly, we need to have some sort of rate metric that quantifies, instead of how many flops we're solving, but just how many like unknowns or equations we're solving. And so we notice that the intensity is not really related to the time to solution, but the rate metric is very dependent on time to solution. And so this spectrum is useful for letting us look at hardware utilization and algorithmic scalability. And so three different examples here. We could look at different software solvers, like for example, the PETSc and Firedrake. They're both finite element packages. There's also various implementations of the multi-grid solvers. And also there's many hardware architectures out there. Like you have the KNL and then the typical Xeons. And then the last thing is like we want to also look at different numerical discretizations, like the Galerkin method versus the discontinuous Galerkin method. But the issue with using this spectrum on the last bullet point here is that it is incomplete. There's a problem with just using the spectrum alone, because we know that not every degree of freedom is the same when it comes to these various discretizations. And some methods have different levels of numerical accuracy, numerical convergence rate. So we need one more rate metric that will now take accuracy, numerical accuracy. And so that's where Matt and I and Richard and another PhD student at Rice, we have come up with something called the time accuracy size spectrum. And so just the rest of this talk will be as follows. So I'll introduce the TAS spectrum, a little bit of a theoretical analysis, and then I'll come up with two examples to demonstrate as proof of concept. So first, for the TAS spectrum, you only need three things: time to solution, problem size, and some sort of accuracy measure. In our case, it would be the L2 error norm. And so for all three metrics, we know we have some approximation of how these will grow or decrease. So for example, time to solution, problem size, we're assuming here that everything is order n. We're assuming that time is linearly proportional to the workload. And so in this case, we know that D here is the spatial dimension, and then alpha here, that is the theoretical convergence rate of whatever numerical method you're using. And so we're taking the L2 error norm here, and with this, now with these three metrics, we can come up with a new spectrum. And so we have the three quantities of interest, time, accuracy, and size, and with these three metrics, we could come up with three different plots. So we have the mesh convergence at the bottom, which really looks at your size and your accuracy. And so this is just your typical L2 error norm H convergence plots. And then if we just want to look at the time and size, we have what's called static scaling. This is actually not my idea. It's actually, I think, Jed Brown's idea, but he didn't call it this. He called it something else. But anyway, it's a really neat concept where you look at the degrees of freedom solved per time. But then now the last metric we need is we need some sort of accuracy rate. Now looking at how many digits of accuracy we're getting per time. And so the mesh convergence, as we know, looks at basically the inverse of the error. So we're taking the inverse because as we increase the problem size, the error decreases. So by taking the inverse, we now get an increasing metric. And so we also look at static scaling, which is the size per time versus time. And so here, when I'm saying time, I'm referring to the time to solution, which includes both the assembly and the solve time. I'm not looking at other things like the pre-processing or post-processing. And then finally, accuracy rate, you basically combine the mesh convergence and the static scaling, and you now get a new metric. And I'll get more into these three in this next slide. So here are the performance metrics needed. So for mesh convergence, we have this notion of digits of accuracy, digits of size, and just some convergence slope. And so these digits of whatever, we basically essentially take the log of the quantities. And so for the digits of accuracy, we're taking the negative logarithm of the L2 error norm. Digits of size, we're taking the log of n. And then the convergence slope, we can now see whether our numerical method we can verify whether it is right or not. And so static scaling here is where we look at the degrees of freedom or the size over some time, and we kind of know that it should be constant. It should be a flat line because they're both increasing by some factor of h to the power of minus d, but I will show you when this will not hold true. So accuracy rates, this is the meaty part of this talk. So the digits of efficacy is something that is Matt here? No, he's not here. All right, sweet. Okay, so the digits of efficacy, it's basically Matt and I, oh, hi Matt. Okay, anyway. So we came up with the negative logarithm of the error scaled by the time to solution. And so basically, the smaller the product of the error in time, the better. And so there's another metric called true static scaling where we basically take the original static scaling but scale the DOF count by how much each degree of freedom contributes to the overall numerical accuracy. And so the accuracy rates, there's two of them, but I will get a little bit more into the theoretical analysis of this. But first, I keep saying static scaling. What is static scaling? So, so before I talk about it, I need to talk about strong and weak scaling. So strong scaling, you fix the problem size but increase the concurrency. Weak scaling, you increase both. Static scaling, you kind of is the reverse of strong scaling. You increase the problem size but you fix it concurrency. And you basically document the degrees of freedom solved per second. And the objective of these kind of plots is to really find what is the optimal range of problem size for a given concurrency. So if you have a machine, you want to know basically roughly how many degrees of freedom will you get order n scaling. Now, if you're, for a given concurrency, if your problem size is too small, then you will kind of see kind of a downturn here, which we will call the strong scaling limit. And so obviously we want a DOF over time metric to be as high as possible, and we want to see that as we increase the problem size, we get a flat slope. But as we increase the problem really large, if it's too large, then we might start seeing some weak scaling memory effects, because then the problems will be, because your computing resources are fixed, so if the problem's too big, then you'll run out of memory, you have a lot of cache misses, or if if your solver preconditioner choices are not optimal, you might get some suboptimal algorithmic convergence, and then you also see a downturn. And so, but now let me talk about digits of efficacy. So basically, when you take the product of error and time, you can now figure out how alpha and d will affect your slopes. And so based on this derivation, we can see what we would expect if we had a 2D problem, which is on the left, versus a 3D problem on the right. And so basically, let's assume we're looking at 3 different algorithms that have order rate convergence rates of 2, 3, and 4. Now, if I'm looking at a second order method with a 2D problem, I should expect to see a flat curve, assuming that I have order and scaling. Likewise, if I have a 3D problem, but also with a second order convergence rate, I will now see a negative slope. And so this is something to keep in mind when you are going up in spatial dimensions, going from a 2D problem to a 3D problem. So don't be surprised, for example, if you see your standard of Galerkin finite element method going down when you are doing a 3D Poisson problem, for example. And so the true static scaling metric, so basically we take the digits of accuracy over the digits of size, and we multiply that by the degrees of freedom per time, and then we come to these this final equation here, and we notice here that as h size approaches 0, then that fraction will approach alpha over d. And so we can see here that if we have a really coarse mesh, and so the red line is the standard static scaling metric, then we see that the first fraction will really skew the data points. But as you refine the mesh, as you get closer to 0, then we will see that the true static scaling lines will meet the ratio of alpha over d. And so this is another thing to pay attention to when you do such analyses. But then also, if you decide to do both digits of efficacy and true static scaling, you want to be able to understand what do these different metrics mean. So, for example, if you have a really high digits of efficacy and high true static scaling, then you know that's a great algorithm. Likewise, if you have low both numbers, then that's bad. But here, the difference really between these two, in my opinion, is that high digits of efficacy really is an indicator of how accurate your algorithm or solver may be. Whereas the true static scaling is more of an indicator of how fast you process the digits of accuracy. And so we'll see how these two metrics can be very useful in this first example here, which is the very difficult Poisson's equation. And so here I'm using the Firedrake project library, which is a really great software, by the way. And so I'm doing the methods of manufactured solution, and I'm looking at the continuous Galerkin and discontinuous Galerkin methods, and I'm doing one P refinement. So I have 4 test cases, and I've set up these problems such that all 4 discretizations have the same degrees of freedom count. That way, because then basically the computing work that needs to be done is roughly the same on this compute node, on this iMac that I have. So I'm using 4 MPI processes. The DOF count ranges from 30,000 degrees to 4 million degrees of freedom. So the first thing we want to look at is the mesh convergence. And so we see here that the red and black line at the bottom are the first order methods, which have a second order convergence rate. But because it is a 3D problem, the slope I will get is not unity, but it is 2 over 3. And we see that the red and blue lines have that slope, whereas the DG and CG2 methods have a third order convergence and a third 3-dimensional problem. And so we see that we have a unity slope. So this mesh convergence verifies that Firedrake is working for my problem. But now let's look at static scaling. So static scaling is the degrees of freedom solved per second. And so now we see here that for all 4 test cases, we see a flat line. So we are in this optimal scaling region. And so that is good news. But what's interesting here is that even though all 4 algorithms have the same DOF count, the first order methods appear to process the degrees of freedom faster than their, third order counterparts. But again, this does not take into account numerical accuracy. So what happens if we look at digits of efficacy? So now digits of efficacy is just simply the L2 error norm scaled by the time to solution. And now we see that it is, in fact, the second order methods that have the higher metrics. And furthermore, we see that the lines are flat, which is consistent with what we had predicted earlier. And then our CG1 and DG1 methods, the slopes are going down, and they're also pretty low. So this is an interesting take on, or I guess you could say, a reversal of the observations made in the subfigure B. Sorry. And now we could also look at the true static scaling, and where we scale every degree of freedom by its contribution to the overall numerical accuracy. And we see here that the CG2 is still, again, also the highest, just like the DOE figure, but we also see that the first three lines, except for the DG2, are roughly in the same ballpark. So this is indicating, at least to us, that we are processing the degrees of freedom at a decent rate. But of course, all of these data points can change if you tune the solver parameters. Okay. And so second problem here, we are looking at, again, the Poisson's problem, but now we're going to look at a really, really large problems from 2 million degrees of freedom to 13 million. We're using 1,000 MPI processes. We're using the PETSc DMplex data structure. And so, again, we look at static scaling. We see that even with all these different multi-grid solvers, the first order methods appear to process degrees of freedom faster than their second order counterparts, but the digits of efficacy metric tell us it is the second order, the CG2 algorithms that are faster. And so this is consistent with the Firedrake findings in my previous slide. Okay, so that essentially covers the meat of my talk, but now I'm going to go into some more of an application problem that I guess my former PhD advisor at U of H and my lab mate have been working on. So they've been working on the porous media flows. They've been looking at recently the dual permeability porosity model, where if you have a porous media with distinct pore networks, then you basically have mass transfer between the macro scale and the micro scale models. And so basically the governing equations, you have the balance of momentum and mass, and you have the mass transfer and the boundary condition. So this is a four-field problem, and it is a four-field, basically two Darcy problems coupled by pressure. And so the different discretizations they want to look at are RT0, VMS, and the DG VMS. I don't know why they chose these three metrics, but I'm not the first author, so I'm just going to present it as it is. So basically, they discretize these problems using the Firedrake library, and basically where I came in is I helped them compose some block solvers. So there's really two ways to solve this problem. You can either split the two scales by scale. So basically the first two blocks will be the macro scale quantities, and then the last two blocks will be the micro scale. Or you can split it by fields. You can put the pressures in one block and the velocities in another block. So these are just the PETSc solve options. And I think I'm running out of time, but we have the experimental setup here. So again, my PhD advisor and his student, they came up with this analytical problem through the method of manufactured solutions. So we are using Firedrake again, but now we're also looking at tetrahedron elements and the extruded hexahedral elements on their Haswell node. And they're using 16 MPI processes up to 1.8, nearly 2 million degrees of freedom. And so for the Mesh-convergence plots, they see that we get basically a second order convergence for the CG and DG methods. RT0 on the tetrahedron, you're getting first order convergence, but for some reason, you're getting superlinear convergence when you use the RT0 on the hex element. Okay, probably. And then so now if you look at the static scaling, now we see here that the RT0 appears to process, okay, so the y-axis should say degrees of freedom per second, not digits of efficacy. So it appears that the degrees of freedom processed by these two solve options appear to favor the RT0 element. But now what happens if we look at digits of efficacy? Instead, now we see, because we know that RT0 has a really low accuracy, we now see that the CG VMS method actually beats out everything else, beats out the other two algorithms. Likewise, but now for the hexahedron elements, because we're getting the super linear convergence for the RT0, now we see that the accuracy is now really affecting the digits of efficacy. And so that is really the end of my talk. So basically the TAS offers additional insight into performance. It's really simple to use, only needs 3 metrics. And I think it's useful for comparing different discretizations. Of course, there's a lot more that can be done. So we want to look at time-dependent PDs, and we really want to be careful of how we present time to solution. So like we need to show like the assembly time, solve time, et cetera, and of course, look at larger problems. Thanks.
Okay, time for a quick question. Rob?
Yeah, your RT0 business on this last slide, when was that run?
This was run like 2 weeks ago by this PhD student.
Okay, so that would be after all of the TSFC, sum factorization business.
I guess so.
Okay, so you probably will find, I don't know, did Knepley put in, would he have been getting a diagonal mass matrix for the RT0?
Kinda, sorta.
Okay.
So the stuff which works out the form and the loop to do is with diagonals. You get a diagonal loop. But that doesn't extend to then constructing a local tensor which is smaller. So you're still going to insert all the zeros. Now you will drop the zeros at another point, but your local size will still be wrong. So we, and similar thing reads over to when you delta cancel on vector and tensor elements. So one of the things that's on the to-do list is to find a mechanism by which you can specify effectively sparse local tensors so that we don't have that problem.
Okay. Okay, in the interest, if you have more questions, hassle him over coffee. He likes having lots of hassle.
Yes.
And hard questions. Harder the better, isn't that what you said? Yeah, thanks again. Okay, so the next speaker is Douglas.